Welcome to another video on molecule simulation using Gaussian software package. In the last video, I have simulated carbon dioxide and I have shown you all the procedures to optimize a structure. How can you optimize them? And I have found the optimized output. And today I will show you how to analyze different parameters from this optimized output. First of all, you will get three files after optimization, which are a CHK format file. This is the output structure, and this is a input structure we have given in the previous video. And this is the output text file, which contains some information regarding average bond length and these types of things, and also some spin states, and you can check it. Okay, so I will show you how to analyze them. Firstly, I am opening the CHK file. After optimization, you will get a linear structure. There it is, perfectly linear structure. And now we will start analyzing. Okay, so I'm enabling the options of symbols, carbon, oxygen. Okay, so now I want to show you the result. To find the result, we will go to the result and then summary. You will get the information related to the energy, ground state energy, at which energy carbon dioxide is formed. And this energy is the electronic energy of the system, the total electronic energy, which is given in the form of Hartree. If you want to convert the Hartree to any conventional units like electron volt, then multiply the Hartree value by 27.2114, and thus you will get the electron volt value. So these are the informations you can get from here. Also, you can check the dipole moment of this system here, and we will also see the electronic properties like charge distribution of the systems from the option result charge distribution. Here we can see that. Okay, so here you will find different types of charge options like Mulliken charge distribution. You can enable the option show numbers. Then you will find the distribution of charge in each atoms. Here, the negative value of charge distribution means there are abundance of electron, and here, if the value is positive, this means there are a deficiency of electrons and in the charge distribution or charge sharing process. So we can found these types of information from here. And now another thing is NBO charge distribution. This is also a similar parameter to Mulliken charge, and it will also give you the information of charge distribution between the atoms in the molecule. You can see that here for oxygen, the value is minus 0.508, and for carbon, it's 1.016. If we take large systems, the distribution of charges between different bonds and atoms will not be the same, and that's why you will also find different values in different portions of your system when the system is large and the molecule contains a more number of atoms, and thus we can analyze it, the charge distribution. There are also some other options, like if you want to see the the distribution of orbitals, you can just go to tools and then go to the option molecular orbital distribution, and from here you will find the HOMO-LUMO gap. Actually, what is HOMO-LUMO gap? HOMO means the highest occupied molecular orbital, and the LUMO means the lowest unoccupied molecular orbital. You can see that here the charge distributions are given. So in the HOMO, this is the energy state up to which the electrons are distributed, and this is the energy of that HOMO state. And after that, there are vacancy of electrons, and this energy state is called the LUMO state, lowest unoccupied molecular orbital, and this is the energy of this LUMO state. So again, these values are given in Hartree. You have to convert it to electron volt. You can just multiply them by 27.2114, and then you will get the result. That's it. And if you want to just calculate the band gap, which is the energy gap between the HOMO state and the LUMO, you will just subtract the energy of HOMO from the energy of LUMO, and then you can easily determine the energy gap, from which you can understand how much energy is required to go from the HOMO state to LUMO state, or in other words, we can say in a sense that from the valence state to the conduction state. Okay, so these are the things you can get from this optimized output. Now, I want to open the log file, which is the text file. From here, you can find the data, like you can find the optimized parameter, which contains the bond energy, bond angle, these types of things. I'm searching it. Optimized parameters. So you can see here here are the optimized parameters. The R symbols are for bond lengths, and R1, R2 are the bond lengths, and A is for bond angles. So there is only a one bond angle, and which is, you can see that 179.998, almost 180. This is the angle, and the bond lengths are 1.1932 and 1.1933 between the carbon and the oxygens. And we can calculate these parameters using these output files. So that's all for this video. In the next video, we will see how we can determine the thermodynamic properties, and how to analyze it. So bye everyone. See you soon.